Right, welcome to our third and final part for day one of electric currents. So in this one, we're going to start looking into resistance. So this is going to be a really important aspect related to electric currents. So in our first video, we talked about the battery and kind of what it's going to do for a circuit by creating a potential difference. In the second video, we looked at, introducing the actual definition of an electric current. And in this third one, we're going to introduce this thing called resistance. So let's go ahead and do that. So to introduce ourselves to resistance, we need to go into something that is known as Ohm's law. So Ohm was this guy, and he did some experiments, and he found that current was proportional but not exactly equal to the potential difference inside of a wire. And, right, so unit-wise, that checks out. Our potential is in volts, which is a Newton times meter per coulomb, whereas our current is coulombs per second. So the units don't match at all. So they can't be exactly the same, but they were proportional to each other. And so what Ohm tried to do is figure out how are they actually related to each other. And so he found that if you reverse the sign of the voltage, so you flip the direction the battery was plugged in, it doesn't affect the actual value for the current. It just changed the direction. So there's something inside of, just this wire and battery that's making it so the current and the potential are not equal to each other. And that something is called resistance. And the variable we're going to be giving it is a nice capital R. Lowercase r for distance, capital R for resistance. And it's this resistance that makes it so the two aren't the same. So we need to think about how do we include resistance in our equation, and we need to figure out what resistance actually is. And before we get into that, I just want to let you know these three symbols here are these symbols that you would see inside of a circuit for a resistor, which is indicative of resistance. And we're going to be using this middle one, so the angry sawtooth shark thing here. So and we'll be seeing this in pretty much every circuit we get into once we get into circuits. But right now, it's just a symbol. So this, because it's in everything, it makes sense that it's going to be something we would be able to observe in a lot of different situations. And before we get into what exactly it is, we just want to really briefly cover Ohm's law. So Ohm's law is given here. So potential is equal to current times the resistance value. And it's this Ohm's law that we are going to be using time and time again as we build up into circuits. And we're going to see a couple of different ways in which resistance is dealt with in this particular video. So how to calculate it and where it comes from. So we are going to be making some assumptions for resistance. So this graph here shows us the current as a function of potential. And if we do this simply by rearranging Ohm's law, we would find the slope is going to be equal to 1 divided by the resistance value. And this is going to be an important idea is that we're assuming that this is going to be constant through the material regardless of the potential or the current flowing through it. And what this means is because we're making this assumption, it means it's not true, right? And if it's not true, that means Ohm's law is not really a law. And in fact, Ohm's law really should just be called Ohm's really nice approximation, because it roughly works for metals. But the second you move away from having a pure metal situation, Ohm's law no longer accurately can describe what you have happening. So what is this resistance? It's really important. It's related to current. It's related to potential. It's roughly constant for materials. So what is it? Resistance is this idea, and it is something that is actually there, that electrons can't really move 100% freely. An electron can run into another electron. Electron can run into one of the roughly stationary atoms inside of our wire. It can run into the edge of the wire. It can, do any combination of these. There's other things I'm sure it can run into. And so with this, right, it's kind of like friction inside of the wire. It's not exactly the same, but it's kind of this idea that you're not actually able to move without putting some effort into it. In this case, the electron's putting effort of overcoming running into literally anything and everything it can. And so with this resistance, there's going to be a couple of different things that influence it. We'll get to those a little bit later, but first we want to look at the SI unit for resistance. It's going to be ohms. It's this capital omega letter, Greek letter, and it's a volt per amp. So something I just want to show you guys is what my ohms are going to end up looking like, because they will definitely not look like that. Mine are a lot more not symmetrical. So anything kind of along these lines is what you can expect for me to draw as an ohm. And I'll fix this picture here so it's not covering the text in the pre-lecture version. So if you were looking at a real resistor, you might see colors or bands on side of the resistor. And what that does is just tells us the resistance value inside of our resistor. Because maybe you don't want to have, for your particular potential difference, you don't want to have the maximum current possible. You can add a resistor into your system, and that will reduce the current value. Now do not, the textbook doesn't have any questions on this. We're not going to be doing any in-person labs where we need to try to dissect this. So there's no need to memorize it. I just wanted to bring it up. So they do exist. In general, all companies use the same colors. It is very difficult to tell the difference between some of the colors as somebody who's trying to figure it out. So it's there. We're going to be ignoring it for this class. So let's go ahead and do an example. So this is number 10 from the back of the chapter. So here we have a battery. It's connected to a bulb, and we want to find the electrons leaving the battery per minute. So we have a couple things given. We have potential, so 4.5 volts. We have our resistance R, 1.3 ohms. We can use Ohm's law in this case to help us start figuring out information about electrons leaving the battery in a minute. So Ohm's law is potential is equal to current times the resistance. So we can rearrange and solve for the current. The reason we want to do this is the current is a charge per time. So what we can do is we can find out electrons have a charge. We can have us use that to help us find the charge for an electron. And in fact, the charge for an electron is 1.6 times 10 to the negative 19 coulombs. So that's going to help us get rid of the charge part and convert it to electrons. And we know that 1 minute is equal to 60 seconds. So we're going to be able to convert our coulombs per second to electrons per minute through using Ohm's law. So let's go ahead and let's actually find the current value. So we're going to have 4.5 volts divided by 1.3 ohms. So our current value, when I plug that in, I got 3.4615 amps. I'll make sure that looks like a 4. So I'm not done here because I want to find the electrons leaving the battery per minute. So in the next slide, what we're going to do is we're going to go through and we're going to convert to our actual answer. So again, our current was given as 3.4615 amps, or 3.4615 coulombs per second. So to get rid of the coulombs, so I've just written it out. Let's do the coulombs first. So a coulomb, I want this to be in terms of electrons. So 1 electron is 1.6 times 10 to the negative 19 coulombs. So this is going to get our coulomb number to, or our coulomb unit to cancel out. And now if we plug this in, we'd have we'd have electrons per second. We didn't want electrons per second, we want electrons per minute. So we know there's 60 seconds in 1 minute. So this is going to be how we can go through and solve for the electrons leaving the battery per minute. So taking this and plugging it in, I got 1.298 times 10 to the 21 electrons per minute. Or if I want to round it to the correct number of SI units, the correct number of sig figs, in this case, which is 2, it'd be 1.3 times 10 to the 21 electrons leaving the battery per minute. So even though our current is a small number of amps, 3 typically isn't seen as a very large number, we have 10, so you have 1.3 times 10 to the 21 electrons leaving the battery every 60 seconds. So when we're looking at electricity, we are looking at huge numbers of electrons moving at all times. So now what we want to do is we want to spend a little bit more time figuring out how can we calculate resistance if it is not explicitly given. And so for that, we need to look at this idea of resistivity. So resistance, again, is constant when we're going to be dealing with Ohm's law. And there are situations where we have to actually go through and calculate it. So in this chapter, we're not going to be, we're not really using circuits, so we actually have to calculate our resistance. Once we get into circuits, we will be dealing with resistance values that are given. So right now we actually have to calculate it. Moving forward, we probably, and by probably, we won't be doing it once we get into the circuit. So this equation here is going to allow us to calculate the resistance. It's equal to rho, which is our resistivity, which is in table 18.1, which we'll look at, times the length of the wire divided by the cross-sectional area of our wire. So if you think about most of the wires you've seen in your life, they're probably circular in shape. Circles are a lot easier to make than hexagons or any other almost nice shape. So the cross-sectional area of the wire is primarily going to be pi r squared, because again, we're going to be dealing a lot with circular wires. So pi r squared is going to be popping up a lot if you're not explicitly given a area value. So this table here is table 18.1. You'll be seeing it a lot this chapter when you're going through and doing calculations. So on the leftmost column, we have our material. It's separated out into conductors, semiconductors, and insulators. We are going to be sticking a lot in the conductor section of our materials. The second column tells us our resistivity. So we're going to be using this to calculate the resistance. So we can see that conductors have much smaller resistivities compared to semiconductors, let alone insulators. So glass has an extremely high resistivity. It's going to be really hard to run an electric current through glass. Whereas if we look at, let's say, aluminum, it's going to be way easier to do that. And we'll talk about this momentarily, but this is the third column is the temperature coefficient. And the temperature coefficient is going to be used to calculate how the resistivity can change with temperature. So we're going to go ahead and we're actually going to do an example before we get into our temperature dependence. So this is number 89 from the back of the chapter. What I'd like you to do is go through and pause the video and think about how can you go through and solve this and set it up and get ready to do that. So we have a couple pieces of information that are given and some that are not. So first, when we're going to be looking at the area, we only want to be focusing on where we actually have metal. So when we have our area of our tube, we have the area of the outer part minus the area of the inner part. Because we want to subtract out this middle section of our wire where there's not actually any wire. So the area we're going to be using, so the area of a circle is pi r squared. So we're going to have pi radius out squared minus radius in squared. So again, the reason we're using this equation for our area is we only want to consider where we actually have metal. And so in order to do that, we have our full wire subtracting out the center part that we've hollowed out. So we now have the area portion. And we have our two radius values. So the diameter out is 5 centimeters, which means that radius out is going to be half that. And we want everything to be in SI units, so we'll have 0.025 meters. We then have our diameter of the inside, which is 3.00 centimeters. So the radius of the inside, again, we need to half that and then convert to SI units. So that's going to be 0.015 meters. Now, here I've gone through and I've used the radius values. It is perfectly valid and equally okay to say pi over 4 and then have diameter out squared minus diameter in squared. Both of these equations work out to the same result. I just personally know that if I don't convert everything to radius values, I'll miss one and I'll screw it up. Or I'll forget the 4 that needs to come because diameter is twice that of the radius. So if you would rather use the diameters, you're welcome to do that. It's 100% up to you. But again, I prefer to use radius values because I will mess up one or multiple of my things. So now we have everything related to the area figured out. We're explicitly given the length of the pipe. It's 10 meters. And if we look at table 18, I don't know why I put everything as chapter 17. We're in chapter 18. Our resistivity from table 18.1 is 1.68 times 10 to the negative 8 ohms times meters. So now we have all of the information we need in order to go through and solve for the resistance of this particular pipe. So let's go ahead and do that on the next slide. So our resistance, the equation is resistivity times length divided by area. And again, we found a new equation for our area. It's going to be pi outward radius squared minus the inward radius squared. So I have all my values. I can go ahead and plug them in. So my resistivity, again from table 18.1. So 1.68 times 10 to the negative 8 ohms times meters, times my length, so 10 meters divided by pi. My outward radius, again, this is the radius value, so my 0.025 meters minus 0.015 meters. I need to make sure I square both of those. When I took this and plugged it into my calculator, the resistance that I got was 1.3369 times 10 to the negative 4, oops, it's an ugly 4, negative 4 ohms. Or again, if I want to convert this to the correct number of sig figs, 1.34 times 10 to the negative 4 ohms. So in this question, what we've done is we've solved for the resistance of a not super nice shape, right? In this case, we had to go through, we couldn't just use the area of a circle because we had a circle with a circle cut out of it. So that meant we needed to change our calculation for the area. And once we did that, we made sure everything was in SI units. We were able to go through and solve for the resistance value. So there is some temperature dependence on resistivity. So when we're going to be using Ohm's law, again, we're going to be assuming that it is a constant value. And the reason we do that is it just makes our lives a lot simpler. But in reality, as temperature increases, so does your resistivity. And the reason that's going to be the case is your atoms have more thermal energy because it's now a hotter wire. The internal energy is higher, therefore it's going to be able to move around a little bit more. And so you're going to have a higher number of collisions for your electrons, which means that it's going to be harder to travel from one location to another. So this equation here tells us how the resistivity changes as a function of temperature. So here we have the resistivity at some temperature T. Here, when we're talking about temperature, we are referring to it in terms of degrees Celsius. So if we go back and we look at table 18.1, everything is in terms of degrees Celsius. So we need to make sure that if we have a temperature, it's in Celsius. It's going to be equal to P0, so this is the resistivity at 20 degrees Celsius. And that's going to be multiplied by the quantity of 1 plus alpha. So we saw alpha in table 18.1. Here's how you would use it. It's the temperature coefficient times the change in temperature. So we have our new temperature minus the 20 degrees Celsius, so our reference temperature. So basically we just have one extra step we would need to go through and do in order to calculate resistance. We would need to count our new resistivity value. We'd calculate this, then we can plug it in to our resistance equation for related to resistivity. So it's just kind of one extra step that we need to go through and do. So something that's interesting is if you look at table 18.1 again, semiconductors and metals actually have different behaviors when it comes to increasing temperature. This has to do with the fact that a semiconductor can change between an insulator and my neck needed to pop there. An insulator and I keep wanting to call it a capacitor. An insulator and a conductor based on a couple of different criteria, and one of those criteria is temperature. So as the temperature increases, it actually gains more electrons that are able to move around freely. All right, so now we're going to do number 22 from the back of the chapter. I've included the relevant information for resistivity and temperature coefficient here. So what I'd like you to go through and do is solve this question. So in this situation, what we're doing is we're trying to find out when the resistivity of aluminum at some temperature is going to be equal to the resistivity of tungsten at 20 degrees Celsius. So I'd be tungsten naught. So right now what I just need to do is go through and plug in some information. So I know the resistivity of aluminum at some temperature can be replaced with the equation of resistivity of aluminum at 20 degrees Celsius times the quantity of 1 plus alpha aluminum T minus T naught, and that's going to be equal to the resistivity of tungsten at 0. So I need to rearrange my equation to solve for the temperature. So going ahead and doing that, I'm going to have tungsten's resistivity divided by the resistivity of aluminum, both at 20 degrees Celsius, minus 1. That quantity gets divided by my temperature coefficient of aluminum plus T0, which is our reference temperature, which in this case is 20 degrees Celsius. So when we're looking at our resistivity table, so table 18.1, this resistivity column is in reference to 20 degrees Celsius. So I'm going to be able to use these values to plug into my equation. I can use the temperature coefficient of aluminum, plug that in. The reference temperature we're going to be using is 20 degrees Celsius, so I can plug that in here as well. So let's go ahead and do that on the next slide. So temperature is going to be equal to my coefficient, or sorry, my resistivity of tungsten, so that was 5.6 times 10 to the negative 8 ohms times meters, divided by the resistivity of aluminum at 20 degrees Celsius. So that's 2.65 times 10 to the negative 8 ohms times meters. I'm going to subtract 1. All of that is going to get divided by the temperature coefficient of aluminum, so 0.00429. That's going to be 1 over degrees Celsius plus 20 degrees Celsius. So it's not the prettiest equation, but now it's just become a plug and chug type situation. So once we plug all of our numbers into the calculator, assuming I've done this correctly, I got 279.4889 degrees Celsius. I want to round this, so based on the question I'm given, I was just told 20 degrees Celsius. I'm assuming that's going to be exactly 20 degrees Celsius, so I want 2 sig figs. So the temperature in which aluminum and tungsten are going to have the same, or aluminum would have the same resistivity. Same resistivity as tungsten at 20 degrees Celsius would happen at 280 degrees Celsius. All right, so that's going to wrap it up for today's lecture. Please make sure to take the lecture quiz if you haven't already, and let me know if you have any questions.